Today we're going to be talking about the perceptron and the structured perceptron. The nice thing about these problems is that they introduce both a fundamental machine learning concept that we'll be using a lot in the future, the perceptron. They also introduce a nice problem formulation of doing structured prediction, where you're not just assuming the same things that we've assumed before. And this is particularly common in applications like vision or, particularly near and dear to me, natural language processing. And so think about logistic regression and support vector machines. And what statistical property do these algorithms share? If you look at the YI predictions of these algorithms, you'll notice that they're all independent. All of the YIs are interchangeable. And this is great. It makes us able to do things like stochastic gradient descent and enables a whole bunch of algorithms as a result and really simplifies our life, but it isn't necessarily correct. In many cases, the world is not filled with independent events. If you're trying to figure out whether a particular credit card transaction is fraudulent or not, it may not be suspicious if you buy $30 worth of flowers from a Hungarian florist online. If you do that 20 times in a day, that may be a sign that your credit card has been compromised. Similarly, when you're saying a sentence, speech recognition depends on the words that you previously said. And if you're doing molecular biology, the context of your genome matters a lot. Or if you're trying to predict suspicious activity on a video camera, if someone is loitering in front of a building for 10 minutes, they might just be waiting for a cab. If they're doing it for 3 hours, that may be suspicious. And particularly relevant recently, many of the predictions that people were making about the 2016 election results were wrong because they didn't take correlation of errors into account. And many of the models had correlated errors, particularly in the Midwest, and they viewed them as independent. So if we're going to do a good job of doing machine learning, we need to have structure in our predictions. So to introduce this task, we're going to talk about one particular application of structured prediction, part of speech tagging. So in part of speech tagging, you want to be able to take a sentence as input and then apply the parts of speech to that sentence. So this is not a natural language processing class, so we won't dwell on what the parts of speech are. Hopefully you remember this from grade school enough. But for instance, saw, in this case, is a verb, but when you see saw again, it's a noun. And so there is often ambiguity in the parts of speech that get used within a sentence, and the job of a part of speech tagging algorithm is to be able to figure out, given the context of a sentence, which part of speech should be assigned to each and every word in the sentence. Traditionally, we assume a number of features that help us decide which part of speech is used for a given word in a context. This is often viewed as a hidden Markov model. If you're familiar with that, we won't be going into that too much in this course, but it's a useful intuition of thinking about how these things might work. So we can think about 3 different classes of features, and we want to find the part of speech sequence Z that maximizes the score, and the score is just the sum of all of these features. For each feature that we observed, it will get a weight that scores how useful this is to a tag sequence Z. And then we have this other function, phi, that just says, is this feature present or not? There are 2 main problems here. How do we move from data to algorithm? This is often called estimation. And then how do we move from a model and unlabeled data to labeled data? And this is often called the inference problem. So you can do estimation doing an HMM. This is relatively easy. It's basically doing the same sort of counting that we did for naive Bayes. And so here, for features that encode how likely a sentence is to start with a particular part of speech, this is just counting up how many sentences start with that part of speech, and then taking the log of that probability because we want to add them at the end. For the transition scores, we again look how many times a noun follows a verb, and how many times a verb follows a noun, and we count all of those up, add in some smoothing, and take the log. And then we also count up, for a given part of speech, how many times does that. Where we need some help mathematically is how, given a bunch of these scores, how do we find the most likely sequence for a sentence? So this is called the Viterbi algorithm, and the way this works is we want to avoid computing all k to the L possibilities, where k is the number of parts of speech and L is the length of the sentence. So what we're going to do is we're going to use dynamic programming to compute the most likely tags for each token subsequence from 0 to t that ends in state k. So you can think of this as memoization. We're going to fill in a table of solutions to the subproblems of our bigger problem. And so the smaller problems are easier than the big problem, so we can put together a bunch of smaller problems to solve a big problem. And if you've done dynamic programming in your algorithms class, this should be really familiar. So the base case is we want to know what is the best way that we could start this sentence. So given the first word of the sentence, what is the most likely initial tag for that very first word? So this is really easy. You look at how often a sentence starts with a particular part of speech, and then you add in how often that part of speech, k, is associated with whatever word you have in that first position. And so here you're just adding two numbers together, and you do that k times, one for each of your k parts of speech. So that's your base case, and then you recurse on that. And then you build up longer and longer sequences. If you end in position n, what is the highest score tag sequence that ends in part of speech k? To compute this, you look at all of the previous parts of speech j that could have gotten you there. So this is using a previous solution that you've computed, and you're adding in the score of transitioning from state j to state k, from part of speech j to part of speech k. And you add that to your previous score, and then you have to add in the score for ending at this word, whatever word is at position n. And so then you have the score of part of speech k giving you word xn. So that's your score of the subsequence ending at position n with part of speech k. And we've exhaustively searched over all possible parts of speech sequences for the best one, but we've done so in an efficient way by not looking at all k to the L possibilities. The complexity of this is now k squared L. You can see that this is the way it is because you have a table of size k times L, but to compute every cell in that table, you need to do k operations. That's the recursive step that we talked about before. You have this max over all of the previous j's, and there are k of them. So that's k times L. So even though the complexity is k squared L, sometimes you still need all of the cells of the table. This is clear conceptually for sentences like "the old man the boats," where if you just hear "the old man" and you fill in your memoization table, you'd think that old is an adjective. But when you get "the old man the boats," you realize that the old is now a noun and man is a verb. But just knowing the scores is not enough. You also need to know how to reconstruct the best part of speech sequence for your sentence. And for this, you need to have breadcrumbs. And so these are pointers going back so that you can find the best previous part of speech that led you to your current state. So let's see an example of this for the sentence, "Come and get it."